about products of rational expressions, quotients and quotients of rational expressions. So as always, what we're doing is we are taking something that you learned in 6th or 7th grade and we're applying it to variables and complex fractions, really. So, for example, if you had, you'll recall when you were younger, you had problems, you might have had a problem like this. 6/7 times 49/72. Okay? And in this sort of a problem, what can you do? You can cross cancel, right? The 7 becomes a 1, 49 becomes a 7, 6 becomes a 1, and 72 becomes 12. Okay? And so then your final answer is 7/12. Okay, so this lesson is basically using this concept and applying it to more complex variable equations. So let's do a couple of those. So here's the very first practice problem that you have written in your notes. So if you look at the numerator, x squared minus 25, hopefully at this point in time you can recognize that this is a difference of squares. And when we have a difference of squares, we know that's actually quite simple to factor. So that's going to be your first step. On all of these types of problems, you want to factor first. So it is factored as x plus 5, x minus 5. Okay, because when we multiply back, we would get x squared minus 5x plus 5x minus 25. So our middle term gets canceled out. In the denominator, what can you factor out? Well, each term has an x. So we can actually factor out an x. When we take out the x, what's left? Well, there's an x left from our x squared and a 7 there. Okay? In our numerator, on the other, what's being multiplied, the other factor, we can pull out an x. It's very similar to the denominator in the previous problem. So we pull that x out and we're left with x plus 3, polynomial as well. It would be x and x, okay? Because we have an x squared in the front. It's subtraction, so we know that one is going to be minus and the other is going to be a plus. And then we have to think what multiplies to get 15 and subtracts to get -2. Well, that's pretty easy. It's 3 times 5 is 15 and 5 minus 3 is 2, or 3 minus 5 is -2. So we want the 5 to be negative so that we end up with a negative middle term. So x minus 5, x plus 3. And you can always FOIL that to make sure that you did it correctly. X squared minus 5x plus 3x. Combine those, you get a -2x minus 15. So we're good. So now we begin to see all of this cross-canceling that I was showing you earlier. We have an x minus 5 here and an x minus 5 here. We can cancel those out. We have an x here and an x there. Those cancel out. And here we have x plus 3 over x plus 3, which is essentially 1. So those cancel out as well. So now we're just left with x plus 5 over x minus 7. And that's our answer. All right, so we are discussing quotients of rational expressions. So I wanted to give this as an example of maybe a lower level use of this concept. So as you can see, I've got all these prime roots. This is a 7. I accidentally put a tail on it, so I was covering that up. But in order to complete this, we've got to multiply the reciprocal of this fraction here. So we would rewrite our equation 3 times 2 times 5 over 7 times 11. Change our sign to multiplication and write the reciprocal of the second fraction. Okay, and at this point now we can cross cancel. Okay, so now we have a similar problem to the one we did before, but this one is obviously division. So very first thing we want to do, well, there's actually more than one thing we could do first, but the first thing I want to do is I want to factor these so that they look a little bit more reasonable. So I'm going to definitely factor this first fraction first. So I can see that I've got an x in both terms, so I can definitely pull an x out. And what's left is x minus 2 divided by, and in the denominator, we have a negative 8 in the third term, so that negative sign tells me that the signs in my parentheses are going to be different. They're going to be opposite. So I'll have an x plus and I'll have an x minus. Okay, and then I have to think what multiplies to get 8 and subtracts to get 2. Well, 4 times 2 is 8 and 4 minus 2 is 2. So I want my 4 to be positive so that my middle term is positive, and I want my 2 to be negative. And I can FOIL that back out to make sure I've done it correctly. At this point, I'm going to go ahead and change my sign and write the reciprocal of the second fraction. And I'm not going to factor quite yet because I want to make sure I have everything in the right place before I factor. So I'll just rewrite that fraction. And I'll check to make sure I've done it correctly. All right, so now to rewrite the first one in factored form. And then I will factor my second one, x plus 4, x minus 2 times, and now I can just factor this. Well, the denominator is easy, so I think I'm just going to do that first. X parentheses, x plus 5. All right, this one's a little bit more complicated, but it's not bad. I'm sure we can do it. So this shows addition. So both of my parentheses are going to have addition in them because this means the signs are both the same, and this means my signs are both addition. So I'll make my parentheses x plus x plus. Okay, so now I have to think it through. What are the factors of 12 that can add to get 7? So there's 1 and 12, that would be 13. There is 2 and 6, that would be 8. Or we could have 3 and 4. So I'm going to put my 3 and 4 because 3 plus 4 is 7. All right, so now that we have it here, we can start canceling. So I have an x plus 4 up top and an x plus 4 down here. I have an x there and an x here. And then I don't have any more across, but x minus 2 over x minus 2 is 1. So we can just cancel that out. So this whole fraction becomes 1. And so our final answer is x plus 3 over x plus 5. So last week we discussed distance problems where we had 2 people or 2 vehicles or something like that traveling the same distance. This week in lesson 94 we have uniform motion problems where the sum of the distances. We're using the sum of the distances to figure out the answer to our problem. So in the very first example, in your notes, you have a southbound bus leaving Fort Walton Beach at 9 a.m. and then 2 hours later, a northbound bus leaving the same station. Okay, so if you can imagine, you have your bus station, right? And you have one bus heading north and the other bus heading south, okay? And we do have times being related. So the southbound bus left at 9 a.m. and the northbound bus left the same station, but it left 2 hours later. So that means it left at 11 a.m. Okay, so it says if the buses traveled the same rate. So what we know then, that they're traveling at the same rate, we know that the rate of the northbound bus is going to equal the rate of the southbound bus. Okay, and it says they were 352 kilometers apart at 2 p.m. So at 2 p.m., this distance right here, their distance apart is 352 kilometers. Okay, so this guy's traveled, right? And at 2 o'clock p.m., this is their distance. So we know that the distance this bus traveled, we'll call that ds, the distance of the southbound bus, plus this distance, the distance of the northbound bus, equals 352 kilometers. So now at this point, now that we have this equation, we can substitute. And so we know that distance equals rate times time. So we can just substitute rate times time for each of these distances. So obviously we need the rate of the southbound bus times the time of the southbound bus plus the rate of the northbound bus times the time of the northbound bus is going to equal 352 kilometers. Okay, well, what did we know from the beginning? From the outset, we said, well, the rates are the same. And so that helps us significantly. Okay, that's the first thing we want to note. So we can actually just use either the southbound or the northbound. We don't have to specify which it is. All right, so I'm just going to say that the rate of the southbound bus times the time of the southbound bus plus the rate of the southbound bus times the time of the northbound bus equals 352 kilometers. We also know a few things about the time. We know that this bus left at 9, the one heading south left at 9, and this measurement occurred at 2 o'clock in the afternoon. So we calculate how many hours that is. That's 5 hours for that bus. So we have the rate of the southbound bus times 5 plus the other rate times the time for the northbound bus is 2 hours less. So it's going to be 3 equals 352. Well, now we can see that here we just can add these coefficients. The 3 and the 5 are coefficients for the rates. So 8 times the rate equals 352 kilometers. We divide both sides by 8, and we find out that the rate equals 44 kilometers per hour. Okay, so we're going to do the next practice problem we're going to do actually comes from page 393 in your books. It's example 94.3. So all of the examples on your on your note sheet come from your book. So some of them are actually the practice problems from this lesson, but several of them are examples given in your book. And that way, what you can do is you can work through the practice problems that are in your notes and check them with your book. Even the answers, or the solutions rather, for the assigned practice problems for the lesson are found in your solutions manual. So if you get stuck, you can always look through there and try to figure out what area you're stuck on, and hopefully figure it out. Because these problems can be challenging. All right, so we're looking at the second example in your notes that talks about the ships that were 400 miles apart. So this is a tragic accident. You've got these two ships, okay? One is here, the other is there, and they are heading toward each other, okay? And we don't really know how fast they're going. We know that one's going faster than the other, but we do know that the distance apart that they are at midnight is 400 miles. Okay? So this is another instance where the distance of this ship plus the distance of that ship, we'll just call them ships 1 and ship 2. If you add them together, it's going to equal 400 miles. Okay, so just as before, we are going to be able to take this distance equals rate times time, and we can substitute rate times time in place of the distance, in place of the d in the equation. Okay, so the rate of the first ship times the time of the first ship is going to be added to the rate of the second ship times the time of the second ship. And when you add those together, you get 400 miles. Okay? We do know that one ship is going to equal the rate of the second ship plus 20. Okay? Because it says that, it says find the speed of both ships if one was 20 miles per hour faster than the other. Okay, so this shows one of the ships is 20 miles per hour faster than the other ship. The other thing that it tells us is that a collision occurred at 8 a.m. Okay, so at midnight, this was their distance. Okay, this distance happened at midnight. Okay, and this collision occurred at 8 a.m. So we know that our time equals 8 hours. Okay? And time is going to be the same for ship 1 as well as for ship 2. So that helps us out. That shows us that we can just equate these times. Our times are the same. So that makes things simpler. Okay? So we have the rate of the first ship times time. I'm not even going to name it because our times are the same. Plus the rate of the second ship times time. Okay? So we have the rate of the first ship times time. I'm not even going to name it because our times are the same. Plus the rate of the second ship times time equals 400 miles. Now what I'm going to do is instead of putting R1, I'm going to substitute R2 plus 20. Okay? Now, this is going to have to be in parentheses multiplied by time. Okay? So R, instead of R1, we're going to say time times R2 plus 20 plus R2 times T equals 400. Okay, our t's are 8. Okay, so now we're going to just substitute 8. 8 times r2 plus 20 plus 8 r2 equals 400. Okay, distribute that 8. 8 times r2 plus 160 plus 8 times r2 equals 400. And now we simplify. 16 times the rate of the second ship plus 160 equals 400. Subtract 160 from both sides. 16 times the rate of the second ship equals 240. If we divide both sides by 16, we find that the rate of the second ship equals 15 miles per hour. Okay, now that we know the rate of the second ship, we can substitute it here. So the rate of the first ship equals 15 plus 20, so it equals 35 miles per hour. We have graphed linear functions already. So you'll recall that a linear function is a straight line. So, and we've graphed them, we've looked at this form, f of x equals mx plus b, or y equals mx plus b. It's the same thing. Okay, but in lesson 94, we are gonna move into, I'm sorry, this is lesson 95. We're gonna move into graphing nonlinear functions, okay? And the main point that is coming across in this section is that we want, you need to be able to recognize different types of nonlinear functions. So they all are identified by just different shapes. So for example, f of x equals x squared. It's a quadratic, so it's going to be a parabola. Okay, so on your practice sheet, all of the equations on this page are this first row. Okay, and so for each one, you're going to want to create your XY chart. Okay, so when x is 1, y, or f of x, will equal 1, because 1 squared is 1. When x is 0, y is 0. When x is negative 1, if we substitute negative 1 in there, we get 1, because negative 1 times negative 1 is positive 1. Okay, and when we graph this, I'm going to start with the 0, 0. Okay, when x is 1, y is 1. When x is negative 1, y is 1, and we can see that this forms a parabola. Substitute other numbers. When x is 2, y is 2. When x is negative 2, y is positive 4. Not 2, but 4. When x is 2, y is positive 4. When x is negative 2, y is positive 4. Okay, so what happens when we change it up a little bit? Okay, what if our function is x minus 3 quantity squared? How does that change our graph? Well, I took the liberty of choosing different numbers for my x value because I wanted to be able to get 0 for my y. So if I put a 3 in here for x, I get 3 minus 3 is 0. 0 squared is 0. And then I chose one number on either side of that x value. So I chose 4, When x is 4, f of x equals 1. 4 minus 3 is 1. 1 squared is 1. When x is 2, 2 minus 3 is negative 1. Negative 1 squared is positive 1. So you can see you're getting the same sort of graph. When x is 3, y is 0. When x is 4, y is 1. When x is 2, y is 1. And if you continued to choose other points, you would see that you have the same sort of looking parabola. Okay, a parabola is going to be symmetrical on either side where this vertex is. Okay, the vertex of the parabola is going to be the lowest point. Okay, this differs a little bit because we're squaring x and then subtracting 3. So when x is 0, what is y? It's negative 3. How about when x is 1? Well, 1 squared is 1. 1 minus 3 is negative 2. When x is 2, 2 squared is 4. 4 minus 3 is positive 1. Let's do a few more points. What about when x is 3? What is y? Well, 9 minus 3 is 6. Okay, let's do a couple of negative points. How about if x is negative 1? Negative 1 squared is 1, and 1 minus 3 is negative 2. So you see there's this symmetry here. All right, so let's go ahead and graph the points that we have. So when x is 0, y is negative 3. When x is 1, y is negative 2. Okay, and we have this corresponding point. When x is negative 1, y is negative 2. And we can go ahead and graph these other points that we have, but we can see that at negative 3 is where the vertex is for this parabola. But let's go ahead and do this one. 2, 1, 3, 6, way up there, okay? And then we can assume, we can know that we're gonna have the same points equidistant away from the origin. Okay, so 2 in the positive direction is a 1, 2 in the negative direction is also 1. And if we wanted to, we could say negative 3, 6. Okay, and that helps us. All right, so you can see that we have the same look on each of these, okay? This is our standard parabola. And when we subtract 3 in parentheses, we can see it gets shifted to the right on the x-axis. And when we subtract 3 outside of parentheses, we can see it gets shifted down on the y-axis. So what happens when we have the opposite of x squared? Okay, well, we know that 0 is going to be our vertex because when x is 0, y is 0. How about when x is 1? Well, 1 squared is 1, but we have a negative out front, so that means it will be a negative 1. Okay? Negative 1 squared is also 1, but we have a negative out front, so it's also going to be a negative 1. So when we graph this parabola, we can see that the only difference is it goes the opposite direction. It opens down. Okay, so once again, the main thing is you have to know what kind of graph x squared will yield you. All right, it's going to yield a parabola. It's going to look like this. And then you have to be able to move it, shift it on the X and Y axis, and you have to know whether or not it opens up or it opens down. It's going to open down if the leading coefficient is negative. It's going to be open up if it's positive. All right, so now we're going to discuss cubic functions. These are going to look very different than parabolas we did before. And I wrote on your paper that you should think they should remind you of disco moves, because that's kind of how they look to me, but not everyone agrees. Okay, so when we have a cubic function, this is the basic cubic function, and this tells you generally speaking what they look like, and they all look like this. If it's a cubic function, it will look like this. When x is 0, y is 0. When x is 1, well, 1 cubed is 1, so there we go. But how about when x is negative 1? Negative 1 times negative 1 is positive 1, times negative 1 is negative 1, okay? And let's just do a couple of extra just so we get a better idea of what it looks like. 2 cubed is 8, and negative 2 cubed, once again, is going to be negative 8, okay? So when we graph this function, it looks like so. There's 0, 0. 1, 1 is about there. 2, 8. It's going to be way up there. You can see it rises really quick. All right, now let's do the negative side. When x is negative 1, y is also negative 1. So about there. And when x is negative 2, y is going to be negative 8, somewhere down here. So let's just put that dot in there. And you can see what it looks like. So the disco moves is this. These are your arms, one going up, one going down. And if you've looked at that poster in my room, you have seen that before. All right, so now what happens? Do you recall what happened with our parabola? You have it right there on your sheet. Okay, when we had something like this, it essentially just moved that parabola over to the right. Okay, we're gonna have the same thing going on with this, except we're gonna move this cubic function to the right. Okay, because when x is 2, y is 0. When x is 3, 3 minus 2 is 1. 1 cubed is 1. What about when x is 1? 1 minus 2 is negative 1. Negative 1 to the third power is negative 1. Okay, so let's graph this. Okay, so when x is 2, y is 0. When x is 3, y is 1. When x is 1, y is negative 1. And we can see that we have the same looking function. It's just been shifted over to. Now, something to think about. What if this were a positive 2? X plus 2, believe it or not, is going to shift over to the left instead of the right. Okay. Here we have f of x equals x cubed minus 2. So let's start with 2. 2 cubed is 8. 8 minus 2 is 6. So when x is 2, y is 6. How about when x is 0? What's y? Negative 2. When x is 1, y is negative 1, because 1 minus 2 is negative 1. And when x is negative 1, negative 1 cubed is negative 1. Negative 1 minus 2 is negative 3. So let's graph that. So when x is 0, y is -2. When x is 2, y is 6. When x is 1, y is -1. And when x is -1, y is -3. So come on down there. Okay. So similar to the one that we did before, we are just going down on the y-axis. Okay. All right, for this last one, unfortunately, there's an error on your paper. I noticed it as I was going through these. There should not be a decimal point before your x, so ignore that. All right, really, this is just the opposite of the cubic function. And just think for a minute, what do you think it will look like? How will this function compare to that function? Okay, get an idea in your mind, and let's see if you're right. So when x is 0, y is 0. When x is 1, well, 1 cubed is +1, but the negative sign makes it negative. So that'll be -1. And when -1 is cubed, you get -1. And the opposite of -1 is +1. So let's take a look at this graph. We have 0, 0. We have 1, -1. And we have -1, 1. All right. So as you can imagine, if we were to graph 2, well, if it's +2, if x is +2, y will be -8. And if x is -2, y will be +8. All right. So here's 2. +2, -8. We're just going to say it's way down here. And when it's -2, +8, which is way up there. Okay. Oops. So you can see that this shape is going to be the opposite of that shape. Okay, so what if we have a function that looks like this? F of x equals the square root of x. So in this case, we want to be careful about what we choose for x. All right, so when x is 0, y is 0. What's the square root of 1? 1. Okay, and then I jump to 4. It's pretty obvious why, because it's a perfect square. So when x is 4, y is 2. Okay, why didn't I choose a negative number? Because we're not using imaginary numbers, actually, is why. So we're only going to choose positive values for x. All right, let's go ahead and graph this. So when x is 0, y is 0. When x is 1, y is 1. And when x is 4, y is 2. So we can kind of see this graph is going to kind of level off a little bit. So the next perfect square that we can think of would be 9. So when x is 9, y is 3. So you can see how that graph kind of starts off a little sharp, but then it levels off a bit. Okay, so this is our basic graph of a square root function. All right, so now what happens when we are shifting this graph? So that's what we're doing here, the square root of x plus 2. Well, when x is -2, y will be 0. When x is -1, -1 plus 2 is 1, and the square root of 1 is 1. When x is 2, 2 plus 2 is 4. The square root of 4 is 2. Okay, and my graph is going to run into this chart, but that's okay. So when x is -2, you can see that we're shifting to the left here. When x is -2, y is 0. When x is -1, y is 1. When x is 2, y is 2. So you get the same look, but it's shifted on the x-axis to the left. Okay? Here we have, this is going to be a shift on the y-axis. So is it going to be an upshift or a downshift? Let's substitute numbers in order to find out. When x is 0, y is 2. When x is 1, well, the square root of 1 is 1. 1 plus 2 rather is 3. When x is 4, the square root of 4 is 2. 2 plus 2 is 4. All right, so when x is 0, y is 2. When x is 1, y is 3. When x is 4, y is 4. And we'll get that slow curve. So now, how would you predict putting a negative sign in front of the square root of x is going to change this original graph? Okay, hopefully you have some thoughts, some ideas about that before we graph it. So when x is 0, y will be 0. When x is 1, well, the square root of 1 is 1, but we want the opposite of that. So y will be negative 1. The square root of 4 is 2, but we want the opposite of 2, which is negative 2. So we can see our graph is actually just going to go in the opposite direction here. So we have a point at 0, 0. We have a point at 1, negative 1. And we have a point at 4, negative 2. So it's going to be reflected on the x-axis. Okay, this is the last type of nonlinear function we're going to look at, and it's an absolute value function. So when x is 0, okay, so we remember that absolute value refers to the distance from the origin to that number on the number line. So we always end up with a positive value for x. A positive value once it comes out of the absolute value. So if we start with 0, the absolute value of 0 is 0. Absolute value of 1, 1. Absolute value of 2, 2. Absolute value of negative 1, when x is negative 1, y is positive 1. When x is negative 2, y is positive 2. Okay, and we can graph that function. 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. So you can see that we have something that looks like a 90-degree angle here. That's how those look. All right, so now let's see what happens when we introduce subtraction in there. What kind of a shift do we have on the x-axis? Well, when x is 2, y will be 0. Because 2 minus 2 is 0. The absolute value of 0 is 0. When x is 1, 1 minus 2 is a negative 1. And the absolute value of negative 1 is 1. 3 minus 2 is 1. And the absolute value of 1 is 1. So this is just going to give us a general idea. If you go over to 2, 0, 1, 1, and 3, 1. Idea that we have another corner, but it's shifted over on the x-axis. And you can imagine if this said x plus 2, we would end up shifting actually in the negative direction. But because it's x minus 2, we shift in the positive direction. Okay, here we have something a little bit different. The 2 is outside of the absolute value symbol. So when x is 0, the absolute value of 0 plus 2 is 2. When x is 1, the absolute value of 1 plus 2 is 3. When x is negative 1, the absolute value of negative 1 is 1. 1 plus 2 is 3. When x is 2, the absolute value of 2 is 2, plus 2 is 4. And when it's negative 2, the absolute value of negative 2 is 2, plus 2 is 4. So when x is 0, y is 2. When x is 1, y is 3. When x is 2, y is 4. And we're going to have, on the negative side, a 3, negative 2, 4. So we see that this is simply a shift on the y-axis. Okay, my dots are not perfect because I'm not on graph paper here. So we see that it's a shift up. Obviously, if this had been minus 2, it would have been a shift down. Okay, so what happens when we have the opposite of the absolute value of x? Well, 0 is still 0, but 1 becomes negative 1. 2 becomes negative 2. Negative 1 becomes negative 1, and negative 2, negative 2. So when we graph this one, 0, 0, 1, negative 1, 2, negative 2, negative 1, negative 1, negative 2, negative 2. And we have the same look, just flipped upside down, similar to how the parabola worked in the negative. Okay, so lesson 96 is about the difference of two squares. So we've actually already discussed this, that if you have something like this, then you take the solution, you find the solution by taking the square root of both sides. Because the square root of p squared is p. Now, we know that the square root of 16 is 4, right? Yes, we do. So, but the small detail is when you are finding a solution and you have something like this where you have a variable is equal to something, it can be equal to positive or negative 4. Because if you put a positive 4 in here and you square it, you get 16. You put a negative 4 in for p and you square it, you also get 16. So if you had a problem such as this, the square root of 9, and you were just supposed to write the answer of that, you'd only write 3, because there's no, they're just asking here, what's the square root of 9? Well, the square root of 9 is 3. So we only use the plus or minus when we have a variable being squared and we're finding a solution for that. So what happens, so 16 is a perfect square, right, of 4. But what if you have something like the next example, p squared equals 41? Well, you take the square root of both sides, and you could find that in a calculator, but since we are not using calculators in this class, we would just write that our answer is p equals plus or minus the square root of 41. Now, what if 41 could be simplified? 41 can't be simplified, but let's say that we did have a perfect square within this square root symbol. So let me give you an example. P squared equals 32. Okay, we can take the square root of both sides. So P equals plus or minus the square root of 32. But then you say, oh wait, 32 is actually 16 times 2. And we know that 16 is a perfect square. So we could simplify that further and say it equals plus or minus 4 times the square root of 2, which is something that we have done before because we recognize that 32 is 16 times 2. And we can take that 16 out as a 4. So we would just put the plus or minus symbol in front of that, okay? Meaning that it equals positive 4 root 2, but it also equals negative 4 root 2. And finish those practice problems.